I kind of come back to the same question that we asked earlier about calculating the pH of a solution prepared by dissolving 0.10 moles of acetic acid and 0.10 moles of sodium acetate in water, and then diluting the solution to a volume of 1 liter. So how do we solve this? First off, uh, I would like you to think about just acetic acid on its own, CH3COOH, just for a second. If that is put in water, and that's going to give you acetate, and it's going to give you hydronium ion. Hopefully you can see that if you knew the concentration of hydronium ion, you would be able to determine the pH of the solution. So if you were to set up an ice problem, you will say initial concentration of acetic acid is 0.1. Of course, acetate as well as hydronium are 0. But if X moles of acetic acid go through the ionization, X of acetate, X of hydronium will get generated. And hence at equilibrium, zero point 0.1 minus X will remain. X of acetate will remain, X of hydronium will remain. So if you were to set this for a Ka, you would say concentration of acetate times concentration of hydronium divided by acetic acid should do the trick. And now I'm going to just substitute the values. Acetate is X times hydronium is X as well. Acetic acid is 0.1 minus X, and that is coming out to be 1.7 times 10 to the power of minus 5. So now you have to ask yourself whether you can use an approximation or not. By all means, what you can use quadratic equation, but it's kind of pointless to do that because approximations work all the time. So again, we are going to choose the concentration, which is 0.1 moles of acetic acid, and it's 1 liter, so it will be 0.1. And I'm going to divide that by the value of Ka and see if that number is going to be greater than 100 or not. And just by eyeball, you can plug this on your calculator, but I can see this is 10 to the power of minus 1. And this is 10 to the power of minus 5. So this is to the tune of somewhere around, 5,000, 6,000. That's a pretty high number. And so we will say that approximation is true. And if the approximation is true, we can say that 0.1 minus X is approximately equal to 0.1. And so one can say X squared divided by 0.1 is equal to 1.7 times 10 to the negative fifth, or X is equal to 1.7 times 10 to the negative sixth square root of that. All I have done here is I have multiplied both sides of the equation by 0.1 and then taken a square root of both sides. I'm just going to do a ballpark because I know that 1.69 square root of that will be 1.3. So this is going to be 1.3-ish times 10 to the power of minus 3 molar. And what was X? X, by the way, was the hydronium ion. So if I take the negative log of this number, I should get my pH. So let's do that. Negative log of this number, 1.3 times 10 to the negative 3. That comes out to be 2.88. That is your pH. So what I know so far is that if I take acetic acid and I take 0.1 moles of it, so this is acetic acid alone, nothing else. So I have a beaker. In that I put acetic acid. I just took 0.1 moles of it and I filled it all the way to the 1 liter mark. That is going to have a pH of 2.88. Now I'm going to set up a concoction. So it's no longer going to be just acetic acid. It's going to be a mixture of acetic acid and sodium acetate. Two things are going to happen. Let me make some room for that calculation. So it's a mixture of sodium acetate and acetic acid. What does that mean? That means that, of course, my acid ionization is going to take place. So acetic acid with water is going to give you is going to give you acetate and hydronium ion. But we also have sodium acetate. And sodium acetate is like sodium chloride for that matter. It's a salt. So the moment you put it in water, it spontaneously will completely ionize to give you acetate and sodium. That means if you begin with 0.1 moles, it is going to give you 0.1 moles of the acetate. What does that tell you? That tells you that you actually are beginning with 0.1 moles of acetate within that beaker. That means how have we generated the solution? We have added 0.1 moles of acetic acid, CH3COOH. We took 0.1 moles of sodium acetate and we are filling it up to 1 liter water. That's what we have done. That means I already have my acetate. The source is different. The source is sodium acetate, but it's there. Molecules, realize, do not have eyes. They don't know what the source is going to be. All we are saying is that initially there is some acetate that is present in the system. And so hopefully you can see that while change is going to be exactly the same, equilibrium value will look like 0.1 plus x for the case of acetate. And so if you had to plug numbers in, it's going to look like 0.1 plus x times x divided by 0.1 minus x. And again, you have to ask how small is x, so whether the approximation holds true or not. And again, the concentrations are 0.1, so for the reasons we worked on before, 0.1 plus x is going to be about equal to 0.1. 0.1 minus x is going to be about equal to 0.1 as well. And you can say that your equation boils down to 0.1 times x divided by 0.1 equal to 1.7 times 10 to the power of negative 5. 0.1 and 0.1 cancel off, and the value of x comes out to be 1.7 times 10 to the negative 5th. And when you take a negative log of this, that will give you pH. So if you try to take a negative log of 1.7 times 10 to the negative 5th, that value comes out to be 4.78 on my calculator. We were at 2.88. We got 4.78. Realize, if you would have added sodium acetate, that means you would have pumped in the acetate concentration. Don't you think that the backward reaction would have proceeded, which basically means that the amount of hydronium would decrease or the pH would increase? And that's what we see, that acetic acid by itself was 2.88. In presence of sodium acetate, the pH rises. We proved our point.